Hello everyone, welcome back. In this particular video, we're going to focus on yet another reaction of carbonyl compounds that is called the Wittig reaction. Now, this is a very important synthetic reaction as far as carbonyl chemistry is concerned. And the reason is because it converts the carbonyl group into a very synthetically versatile functional group, and that is an alkene. So this reaction overall involves a carbonyl compound reacting with a phosphorus ylid, okay, to give an alkene product. And we'll talk more about the ylid and how it's made in a little bit. But here I've captured an overall summary of the reaction. When you react a carbonyl compound here, again, the carbonyl compound here is representative of both ketones and aldehydes. So please keep that in mind. These are groups, they could be carbon-containing groups, which would make it a ketone. One of them could be a hydrogen, which would make it an aldehyde. Both of them could be hydrogens, which would make it a formaldehyde, okay, which would make it formaldehyde. So this structure here is just representative of every carbonyl compound that's possible. So when you react a carbonyl compound with a phosphorus ylid, now a phosphorus ylid has a carbon that's directly connected to a phosphorus atom, and the carbon bears a negative charge. So in some sense, we can say that the ylid, the phosphorus ylid, is actually a carbon nucleophile. Okay, it's a source of a carbon nucleophile. So very similar to a Grignard reagent or alkyl lithiums, if you've talked about those before. So ylid involves this carbon nucleophile. And what happens in the end is that your oxygen from the carbonyl compound is replaced with this carbon, and it forms a double bond. So you get a double bond between the carbon, which was negatively charged, or which was the nucleophilic carbon in the ylid, and the carbonyl carbon in your carbonyl compound, so that your product is an alkene. And along with it, you make a byproduct, which is triphenylphosphine oxide or a phosphine oxide. In this specific case, I've used triphenylphosphine, but if it is not triphenylphosphine, it will be some other phosphine oxide. So that's the overall reaction. And just to understand it a little bit more, before we go into the details, let's look at a few examples so that we can start visualizing what could a carbonyl compound look like, what could a ylid look like, and then what would be the resulting alkene. Okay, so let's say if we start with a carbonyl compound like this, we have a ketone. Okay, 1, 2, 3, 4, 5 carbons. It's a 5-carbon ketone. So specifically, this is 2-pentanone. Okay, this is a ketone. If you react this carbonyl compound with, let's say, CH2, phosphorus ylid, like that. Now, draw some parallel to the structure here. If you look at the ylid specifically, in my ylid, the specific ylid that I've written, both of these R prime groups are hydrogens. You have a carbon with the negative charge, and the carbon is connected directly to a phosphorus. Both R groups are hydrogens here. So if we do this reaction, then our product is going to be an alkene, where, like I said, there is a double bond between the carbon, which bears the negative charge in the ylid, and the carbonyl carbon. So this carbon has 2 hydrogens on it. There's the carbonyl carbon. So that means the alkene that we get is CH2, or has a CH2 group over there. That's the alkene product that we get. Okay, so that's one example. Let's look at another one. Say we have a ketone, and we react this with a different ylid now. Okay, that's the ylid this time, and that's the ketone. So the ylid is the carbon with the negative charge. And now if you consider the bond line structure, the Lewis structure, there is a hydrogen on that carbon, and there's a methyl group on that carbon. So the product that we're going to get here would be that alkene. The carbon, which is the ylid, is now directly connected to the carbonyl carbon through a double bond, and that carbon had a methyl group to it. Now, if there were two methyl groups, you will add two methyl groups. Or if it was one methyl group and one ethyl group, you would basically keep changing. So I hope that makes sense, okay? So I can show that modification right here. So let's say if it were this same carbonyl compound, but the ylid had an ethyl group here, then my product is going to have that carbon with a methyl group and an ethyl group. That would be the product. If this were not a ketone, but if you were to start with an aldehyde, you would just change accordingly in your product, okay? So overall, it's a synthetically useful reaction because it converts carbonyl groups into alkenes. And as we know, alkenes are very useful functional groups because they can be converted into a variety of other functional groups. Okay, there are a lot of reactions, electrophilic addition reactions that alkenes can participate in. So with that brief overview of the reaction, let's talk about the ylid a little bit, and let's talk about its synthesis. How is the ylid synthesized? Okay. So the ylid, like we saw, has a carbon that's directly connected to a phosphorus. Okay, so we had, or we could have something like R prime, carbon connected to a phosphorus. The phosphorus has a positive charge. This carbon has a negative charge on it. Now, in principle, not in principle, we can write a resonance form for this ylid structure, where we can take this double bond and put it between the space, in the space between the carbon and the phosphorus. So it would be almost like resonance in, let's say, a carbonyl compound, although you have to view it slightly differently. In a carbonyl compound, the carbon has a positive charge, and your oxygen would have the negative charge. That's one of the resonance forms for a carbonyl compound. So you can take the lone pair from here and put it in the space between the carbon and the oxygen to get to the a neutral structure for this carbonyl compound, the resonance form. So that's resonance form. So very similarly, we can do something over here, where now we have a double bond between the carbon and the phosphorus. Okay, and we get to that structure, which is the neutral form of the ylid. Okay, so that's the ylid. And I've drawn this carbonyl compound to show some resemblance, how these are related, the resonance at least, how are they related. Now, one key difference though, is that in case of a carbonyl compound or any other structure like this, where you have a second row element, okay, this is an element from the second row of the periodic table. This is also an element from the second row of the periodic table. When you have a resonance form between such elements, and when you have a structure which basically maximizes on bonds, the octets are complete for all the elements that are involved, then the neutral structure here with the maximum number of bonds, this is a major contributor to the resonance. Okay, so this is the major contributor to resonance. Now, if you compare it to the ylid structure, it may seem like, okay, this is also a neutral structure, has maximized on the number of bonds and everything. So this might be a major contributor, but it's not. Actually, the charge form of the ylid, this is a major contributor. Okay, this is a minor contributor to resonance, and this is the major contributor. Now, why would that be so? And the reason is, The double bond that's formed here, okay, so one of these bonds is a pi bond. So the pi bond here involves the overlap of a carbon 2p orbital. The carbon is using its 2p orbital to overlap with a phosphorus 3p orbital. Okay, it's a bond between a carbon 2p and a phosphorus 3p orbital, because carbon is from the second row of the periodic table, but phosphorus is from the third row of the periodic table. And for that reason, this pi bond that's formed, it's not a very strong bond. Okay, it is relatively weak. Now, pi bonds in general are weaker compared to sigma bonds, but this pi bond here, because it is formed by the overlap of a 2p orbital with a 3p orbital. Now, the 3p orbital is bigger, it's more diffuse, which makes the bonding weaker. So because of that, this structure overall is not a major contributor to the resonance here, okay? And the ylids are usually written in this charge form, like a zwitterionic form, where there is a positive charge and a negative charge within the same molecule. The neutral form is not used. But if you see the neutral form written, you're still going to treat it like the zwitterionic or the charged form of it and use it for the reactions. That's how you're going to proceed. Okay, so do not let the neutral form confuse you. That's just the ylid written in a different resonance form. So please keep that in mind. Okay, so that's something about the structure and the resonance that's possible in the ylid molecule. Now let's talk about the synthesis of the ylid. So to synthesize an ylid, you react an alkyl halide with triphenylphosphine, or the triphenylphosphine here, PPH3, this is just representative of any phosphine, some R group on the phosphine. And there is an SN2 reaction between these two, which would give us an alkyl phosphonium salt. Okay, and then the alkyl phosphonium salt is treated with a base to give the ylid. That's the synthesis. So it's a two-step process from an alkyl halide to synthesize the ylid. So let's look at that. Okay. So if we were to write a very generalized example, what we're doing here is we're reacting an alkyl halide, okay, an alkyl halide with a phosphine. Phosphines are strong nucleophiles. Okay, so under these conditions, when you do it, the phosphine can do an SN2 attack. Okay, an SN2-like attack, which means it's a backside attack on the alkyl halide to kick out that halogen. And remember, the attack always happens at that alpha carbon if it's an SN2 reaction. Such that by the end of it, you're going to get, since the phosphorus is using its lone pair to do the attack, the phosphorus would now have a positive charge on it. Okay, and we'll get this species along with the chloride. It's going to be stabilized by the chloride ion. So that's the alkyl phosphonium salt here. Subsequently, and again, you want to keep track of the carbon atom. So that's the alpha carbon, which was connected to the halogen. And I'm using an alkyl chloride here specifically. The alpha carbon is now connected to the phosphine. When you react this with a strong base, now these bases have to be strong. So some examples of bases are N-butyl lithium, or you could use sodium hydride, or you could use sodium amide. So these are all strong bases, okay? So N-butyl lithium has a negative here, the lithium is positive. Sodium hydride has a positive here, the hydrogen is negative, there's a positive here, and the nitrogen is negative. So these are all really strong bases. So when you react an alkyl phosphonium salt with a strong base, what happens is the base deprotonates one of the alpha hydrogens. So one requirement for making a ylid would be that you need an alpha hydrogen, okay? So the base deprotonates the alpha hydrogen, and I'm just pushing the electron, I'm showing the electron push arrows starting from the butyl lithium here, but it could be any of the other bases, okay? It deprotonates the alpha hydrogen. Electrons from that bond go to that alpha carbon, such that in our product, we get PPH3. There's a positive charge on that phosphorus now. And this alpha carbon, or what was the alpha carbon, has a negative charge on it because it has a lone pair. And it still has one alpha hydrogen left on it, but I'm just not showing it in the bond line structure here. So that's how we get the ylid. That's how we get the ylid. Okay, so that's the synthesis of the ylid. Now, as you can imagine, since this first step, okay, since the first step is an SN2-like attack by the phosphine, what that means is everything that we know about an SN2 reaction would apply here. So the order of reactivity, for alkyl halide is methyl, okay, the least substituted alkyl halide is greater, or that's the best actually, than primary alkyl halides, which are better than secondary. And then tertiary do not react under these conditions. So you cannot make an ylid from a tertiary alkyl halide because it is not amenable to this first SN2-like attack. So that's important to keep in mind. So everything that we know about an SN2 reaction really applies here again. Okay, so let's look at some specific examples of ylid synthesis. Example, so let's say if we start with methyl bromide. Let me show one example with a methyl, and you react it with PR3. Again, I'm using a generalized phosphine here. This R is most typically like a phosphine, but it could be another phosphine containing group. So if you react it with a phosphine, the phosphine is going to react with the methyl bromide in an SN2-like manner, and it would give us a carbon phosphine bond. The carbon is positively charged, and I'm going to write the methyl as CH2 with a hydrogen. So I'm just writing it out so that I can show the electron push here. So that's what we get, along with the bromide. So that's the alkyl phosphonium salt. And now if we react it with sodium hydride as a base. So notice in the generalized example, I used butyl lithium. I showed you how butyl lithium would work. But let's say if you were using sodium hydride, the hydride is going to come deprotonate. This was your alpha carbon. This is the alpha carbon. It's going to deprotonate the alpha carbon. Electrons from here would go to that carbon, so that our ylid is going to be PR3 positive and the negative. And notice how we're just writing the charged form of the ylid, but you can do resonance on this and it would convert it into the neutral form of the ylid. Okay, so that would be the methyl ylid. What if we started with let's say, a benzyl containing group. Let's say we had benzyl chloride, and let's use a specific phosphine, PPH3. The phosphine is going to come and attack. That's your alpha carbon. The chlorine gets kicked out. This will give us the phosphonium salt. Okay, so the alkyl phosphonium salt, there's our alkyl alpha carbon, there's the chloride. So that would be our alkyl phosphonium salt. And now, again, let me show the use of butyl lithium. It's like one of the more common bases that's used. So since this is the alpha carbon, this carbon has two hydrogens. We only need to use one. So I'm showing one. So the base here, the butyl base, is going to come and deprotonate that alpha hydrogen. Electrons go to that alpha carbon such that in the end, we'll get PPH3 plus lone pair with a negative charge. So we get the ylid that way. Okay, so those are two examples that demonstrate the synthesis of the ylid. So I hope these are helpful as you're trying to use these reactions. Okay, start from an alkyl halide to make the ylid. Now let's continue on and talk about the mechanism of the Wittig reaction itself. Like, how does this ylid react with the carbonyl compound? That is what we're going to look at next. Okay, so now we're going to talk a little bit in detail about the mechanism of the Wittig reaction itself. How does a carbonyl compound react with an ylid to give us an alkene and get that product, the byproduct, the phosphine oxide? The alkene is a product here. Okay, so the carbonyl reacts with the ylid to give us the alkene. That's the main reaction that we are focusing on. And like I mentioned earlier, the ylid is a carbon nucleophile. It's a source of a carbon nucleophile. Okay, so this is a carbon nucleophile. So the mechanism of this reaction has some elements that are common to what we've seen in previous examples of reactions involving carbonyl compounds, but it also deviates at some points, okay? And it involves the formation of a new sort of an intermediate that we haven't yet encountered in organic chemistry. So what you can imagine is that you have the carbonyl compound. This reacts with the ylid. So the ylid has the carbon with the negative charge on it. Okay, this here is a positive charge, has a negative charge on it. The phosphorus is positively charged. And so since this is the nucleophile and carbonyl compounds, these behave as electrophiles. The first step here involves the attack of that ylid carbon on the carbonyl carbon. Okay, the nucleophilic carbon goes and attacks the electrophilic carbon. Now, as we've seen before, as this attack happens, simultaneously the double bond here is going to open up. Now, in most cases, or in almost all cases previously, what we've seen is that as the double bond opens, it goes to the oxygen atom. Okay, it lands on that oxygen atom. In a Wittig reaction, it is believed that as this pi bond opens up, since there's the phosphorus here, so we're trying to make one bond between the carbons here. The two carbons are coming together, making a bond. Simultaneously, the pi bond here goes and attacks the phosphorus. Okay, so the nucleophile from the ylid attacks the electrophile from the carbonyl compound. That would open up the pi bond so that the oxygen now becomes nucleophilic. It will have a negative charge on it. Now, we don't really see that. in a very concerted sort of a manner, that oxygen attacks the phosphorus, okay, such that you get to an intermediate where you have the carbonyl compound, which had the two R groups connected to it, now bonded to the ylid carbon, which has the R prime groups connected to it. There's the oxygen. This is connected to the phosphorus, ppH3. And since the oxygen attacks the phosphorus, we get a double bond between the phosphorus also. This intermediate is called an oxaphosphatine intermediate. And once this intermediate is formed, this ring that's formed, the four-membered ring, that sort of breaks, okay? The ring opens up. Now, as it opens up, what happens is the double bonds, they form. So the electrons move in a cyclic fashion such that you land a double bond between the phosphorus and the oxygen atom, and a double bond between what was the carbonyl carbon and the ylid carbon. That's how we get the alkene product here. So in the end, you will have the R primes double bonded. So the ylid carbon is connected to the carbonyl carbon through a double bond. And plus, you have the phosphorus double bonded to the oxygen. That's what this triphenyl phosphine oxide intermediate is. Now, the driving force for this reaction is the formation of this phosphorus oxygen double bond. So phosphorus is also an oxophilic metal, oxophilic element, sorry. And so it likes to make multiple bonds with oxygen. So the formation of that phosphorus oxygen double bond, that sort of drives this reaction forward. We will talk about the stereochemistry that's involved in a Wittig reaction in a following video. Bye.